All right, let's get going. So last class we had started chapter 13, and we had begun talking about the area below a surface down like a curtain. And so we had gotten to this problem, and I kind of went off on a little tangent and showed how a line integral, which is what these are called, even though I told you it should be called curve integrals, these line integrals are actually just a more generalization of all the integrals you did in Cal 2. So I got to this one. We didn't do it, so let's go ahead and start here. We have next mini exam is due on Wednesday. At least that's what y'all told me, right? So Wednesday, and then in terms of where we are on the calendar, let's see. Today is the 13th. We're a little ahead. No. Yeah, we're a little ahead, but don't worry, we will fall behind. These sections are long, so. All right, so this one, find the, how do we say it? The line integral over c of 2x with respect to, not surface area. That'll be capital S, that's coming.
Arc length.
Arc length, good, with respect to arc length. So we had a formula for this. We'll scroll up so we can be reminded of what it is, so that way when I put it up here, like, what the hell are you doing? Here it is. The line integral along the line C of the scalar function f of xy ds with respect to arc length is, well, what we have to do is we have to find parametrizations of the curve we're integrating over. We have to find the parametric equations for it. And then what we'll do is we'll evaluate the surface on the x and y parametric equations for x and y. We'll have to plug those into the surface. And then we have to take the square root of the derivative of x with respect to t squared plus the derivative of y with respect to t squared dt. So we get everything written in terms of t. And there was a question about change of variable, and I tabled it. I have an answer, but since he's not here, I'm not going to go into it. So this is called the integral with respect to arc length, right? All right, so here's the example that we were working on. Whoa, I passed it up. Went way too fast. There it is. I think I'll make this a little smaller. Still read that? All right with that? All right, so first thing I'm going to do is realize that we want to go over the curve C, but then it gives us two curves, C1 and C2. So C is made up of both of these curves. So we have to integrate over two separate curves. And so let me try and draw in two-dimensional space, let me draw this domain, which is the C. So let's start here. Let's see, C1 is a parabola, y equals x squared from 0, 0 to 1, 1. So I start at 0, 0, and I go to 1, 1. And it's the parabola, right, like that. That's C1. And then C2 is the line segment that goes from 1, 1 to 1, 2. So that's a straight line segment going from here straight up, like that. That's C2. Stops here at 1, 2. And this point was 1, 1. All right, so the way that line integrals work when you have a curve made up of multiple curves is that you can do them separately. So to do the line integral over C of 2x ds, I'll do the line integral over C1 of 2x ds plus the line integral of C2 2x ds. Now that was in your notes. The note before this was that me explaining that that's okay. All right. So now we need to do each of these. So let's do this one first, all right? The one over C1. So I'm going to look at C1 first. C1 is the parabola, right? And the question is, how do we draw that parabola with parametric equations? So we need to somehow draw this parabola using some function x of t and y of t to draw it. Now, this is going to depend, well, it's probably been a long time since you've done parametric, but the way that we can do a function of x, would you all agree y equals x squared? You can say y is a function of x. The way we do a parametric curve whenever you have y as a function of x is you always just replace the x function. You just say, you call that t, and then the y is that y, but replace the x with t. So this would be t squared. And that will draw you that same parabola. Now, I do have to put restrictions on t, though. You all see I'm getting that from this, right? Okay, so what are my restrictions on t? Well, I want to start at 0, 0, right? So 0, 0, my t would need to start at 0, because 0 here, I get 0, 0. And then where will it end? Well, I need to end at 1, 1, right? So 1, 1. So 1. Okay? That will draw me the curve C1. Questions? Let me put on the board here, on the side here, integral over c of f of xy ds is equal to the integral from a to b of f evaluated at x of t, y of t, and then the square root of dx dt squared plus dy dt squared dt. That's our formula that we're going to be using. So let's do this for C1. For C1, we're going to be doing the integral from 0 to 1. And now we want our scalar function, right? This is our f, right? This is our f of xy. So we want to replace the x with what? T, because that's our x function, right? Our x function has become t, so we're going to go 2t. And then the ds is actually the square root of the derivatives. Now, I haven't done the derivatives, have I? Let me do those real quick. Let me do those. I'll do those in blue down here. I need my derivatives. So I can write it this way. X prime of t is just 1, and y prime of t is 2t. And now I put those in there, right? So it's the 1 squared. And then plus, and then I'm going to have to square the 2t, right? dt. And then this is integral from 0 to 1. We've got 2t integral 1 plus 4t squared dt. And we should be able to do that with a basic u sub. Right? If I let u be this, I should be able to do that. So I'm going to put a check mark here. We could get that, right? Okay, that'll be the answer to the first part. Any questions? Yes?
I see you got the yt. How did you get the x?
Okay, so anytime, these are called the parametric equations for that curve. Anytime your curve is y as a function of x, right? This is a function of x. What you always do in that case is replace, the x of t will always be t. And then the y will be that curve with t plugged in, right? So you're just replacing x with t, and then y becomes the t squared. Do you see it?
Yeah.
Okay. Now, if it were the other way around, just as a side note, if this were our original curve, let's say that was our original curve. Now x is a function of t, right? Then what you do is your x of t and y of t, you do the opposite. So the y of t is t, and the x of t is t squared. Okay? Understand? All right, so I'm not going to do this integral because we could do it, right? We could evaluate that. I'm just going to leave it as an exercise. But we still need to do the integral over C2. So let's go do C2. So for C2, now we're looking at a line segment. That's a line segment. And we did this a lot back in chapter 10. The way to find the vector equation of a line segment, the way to find the parametric equation of a line segment is first to find like the vector form and then convert that to parametric. So since this is a line segment, I'm going to look at this as being r of t, back in old school chapter 10, is r naught plus tv. We had this good old-fashioned, right, where the r naught is your starting point converted to a vector. So what's r naught for us? 1, 1. Plus t times, and v here is the what? direction vector, which is the vector going from where to where? From here to here, right? So to get that, we do this minus this, and then this minus this. So what is that? 0, 1. 0, 1. And then we can put those together. This is just really 1, 1 plus, if you distribute the t through, you get 0t. And then put those together, you should get 1, comma, 1 plus t. And then those are our two parametric equations, the x and the y respectively. So our x of t here is what? 1, and our y of t is 1 plus t. And our t here will go between, careful, 0 and 1. Remember I told you all that anytime you want to come up with a vector equation of a line segment, it'll always be from 0 to 1 so long as you follow the method that I taught, which is your r naught will always be where you're starting, and your v will always be the vector from here to here. If you do it that way, then your restrictions on t will always be 0 to 1. You can check it, right? Check it. Let t be 0. What do you get if you plug 0 in here? 1, 1? Plug in 1. What do you get? 1, 2. That just kind of helps you be confident that that is drawing that line segment. And it goes from 1, 1 to 1, 2. Hey, we're going to need derivatives, aren't we? May as well just do them now. So x prime of t, 0, and y prime of t, 1. There we go. So I think I'm ready. All right, so to do this, I do line integral. I'm doing this one right in here now, right? This becomes the integral from 0 to 1, because those are restrictions on t. And then I have 2 times x. What's x for us this time? 1. It's just a constant, right? It's just 1. Just 2. Square root of, okay, the derivative of x squared, 0, plus derivative of y squared, 1, dt. And that's all just a constant, right? Isn't that just the integral from 0? This one's really trivial, isn't it? 0 to 1 of 2 dt, which is just 2. Okay. Good. Take that answer, add it to the other one. That is the area of the curtain when you take, well, what is it? Let's make sure we see this geometrically. What was our surface up top? What was the equation of the surface up top? 2x. And what is 2x if you graph it? And yes, it's straight line in two-dimensional space, but in three-dimensional space, it's a plane, right? So we have this plane, right? We have this plane. Whoa, shit. You'll see the plane here? That's 2x. And then we have our parabola on the ground and then the straight line segment. If you take just those points and plug them up into the surface, you get that curve on the surface, right? We're dropping a curtain down from there, and we're trying to find the area of that curtain. And I can tell you this so far. We had figured out that this area on C2, that was 2, right? The area of that was 2. And then the area of that one we said we could get, but we never did. Understood? Okay, we're going to continue. All right, there are 2 other line integrals. There's 2 other ones that are used quite a bit. And I think it's not going to make a lot of sense as to why we use these, but just for now, just trust that they are. Here's what they are. The first one is called the line integral along C with respect to x, not with respect to s, right? Not with respect to arc length, but with respect to x. And here's the formula. Here's the formula right here. And you'll notice that the first part of the formula is exactly the same. And do you see the last part of the formula right here? This x prime t dt, you see that? That's what you would get if that was 0, right? If this was 0, then you'd have the square root of the derivative squared, right? Derivative with respect to x squared. Square root and the square would kill each other off, and you just have, this would just be x prime, wouldn't it? That's what this formula is. The other one is the line integral along the curve C with respect to y, which is this formula, which is this with that being 0 this time. Now, what are those geometrically? Let's see. So here's the original problem from when I started this last class. We said, hey, we've got this curve on the ground. Can you all see that? You have the curve on the ground. You have that curve plugged in, and we found the curtain. We found the area of that curtain. And that was the line integral along C with respect to arc length, right? With respect to x, here's the difference. What we imagine is looking at that blue curve, looking at it from this perspective, as if we were standing looking this way. Shit, let go, right there. Do y'all see? We're looking like we're standing way down at like y equals infinity, like really far away. And we're seeing that curve and how that curve would project onto the xz plane, right? That's like the projection of that curve onto the xz plane. And if we project it onto that xz plane, then we are finding the area of that curtain, the gray one instead of the green one. Are they going to have the same area? No. That's the line integral with respect to x. And then with respect to y, what do you think the difference is? Project that blue curve onto the yz plane over there on that side. You see? So it's like there, project it that way, or project it this way. See the difference? And generally speaking, those two answers are different. We should get different areas. Sorry, these three are different results, depending on the geometry, but generally speaking, they're different. There are some cases where they would be the same. That's what they are geometrically, all right? Now, those two line integrals, the one with respect to x, there's the notation. See the notation? It's not ds, it's dx and dy. Those are used so much, so often, that we actually have a special notation for it. So this would be the line integral along C with respect to x. And here I have a function p instead of f of xy. Let's call it p of xy. P is like f, just capital P. And then plus, this one's a different function, q of xy dy. If we ever see that and we want to add these two together, that notation means the same thing. That's just to show you that you don't have to write them as two different integrals. You could write them as a single integral, dx here, dy there, and then use your formulas on each one. So here's an example so we can see that notation in use. Let's find this. Find the line integral along C of sine x dx. So that's the line integral with respect to x plus cosine y dy. So these are basically two line integrals we're adding together. Now let's talk about C. C is the top half of the circle, x squared plus y squared is 1, from 1, 0 to negative 1, 0. And the line segment from negative 1, 0 to negative 2, 3. Do you have a question?
No, I just say that's the unit circle, right?
That is the unit circle, yep. So let me try and draw what this C is first. I just got this marker. What the hell? I swear they're putting dead markers back into the workroom. They come into the rooms, they pick up all these markers, and they just go put them back in. Okay, so let's see. Top half of the unit circle, right? Top half of the unit circle from 1, 0 to negative 1, 0. I'm going to call this C1. Okay, I'm breaking this up into two pieces. And then C2 is the line segment that goes from negative 1, 0 to negative 2, 3. Negative 2, 3 is going to be kind of way up here, sorry. Good enough right there. That's C2. So let's come up with parameterizations. I'm going to do C1 and C2 right now together. Let's get the parameterizations of each of these curves. Then we'll start putting all the integral stuff together. So let's do C1 first. C1. X of t, y of t. Okay, how are you going to draw me a unit circle? Cosine and sine, right? Unit circle, so I use 1 cosine t, 1 sine t, right? Man, this one's dead too. That's a good one. Do y'all agree that will draw the circle? Unit circle? All right, will it start? Well, we need limits on t, don't we? Where does t start? 0, where does it stop? Pi, right? Now, will this work if I let t be 0, where am I? Cosine of 0 is 1, sine of 0 is 0, so I'll be at 1, 0. And when I get to pi, cosine of pi is -1, sine of pi is 0. So that does draw it kind of like in this direction. Now that's important because they say from here to here, right? If it was the other way around, you'd have to adjust that. No, you wouldn't want to change it that way. Let's talk about that after. Yeah, there's a way you can reverse it. So, what do you think? What now? What do y'all want to do? Do y'all want the derivatives now because we'll need them later, or yeah, derivatives now? So x prime of t, negative sine t. Now this marker is real good. Y prime of t, cosine t. Okay, so that's everything we should need for C1, right? Okay, now C2. So for C2, we have a straight line segment again, don't we? Line segment goes from -1, 0 to -2, 3. So to do this, I'm going to go back to the good old-fashioned R of t equals R naught TV plus TV. And R naught for us will be -1, 0, right? That's where I want to start. And then plus t times, I need a vector going from here to here. So, what is it? Careful. You're taking -2 and subtracting -1. -1. -1, 3. Yes, -1, 3. All right? And then put those together, right? See if I can put them together all at one time here. -1 minus t, and then 3t. I did that all at one step. And t will go between 0 and 1, always, right? As long as we set it up that way. All right. So there are my two curves, right? So what I've got to do now is I got to do that integral right there over each of these curves. And I'm going to try and draw it, or try and write it all out at one time. Let's see. Oh, wait, we didn't get derivatives. Sorry. Let's write it out explicitly. X of t here and y of t. X of t is the first component, -1 minus t. The second one, 3t. Take their derivatives. -1, y prime is 3. Constants. Okay, that's great. Yeah, I'm going to erase, I don't know, where do I go? I'm out of room. Right here? Let me try it right here. So I'm going to do, that original integral becomes the line integral over C1, right, of sine x dx plus cosine y dy, plus the line integral over C2 of sine x dx plus cosine y dy. I'm trying to squeeze that in there. Sorry, that's just, you're breaking up into two, right? And now let's go over C1 first. So if we're over C1, what are our limits of integration? 0 to pi. Integral 0 to pi. Okay, what is sine of x for us here, though? So for us, you have sine, what's x for us if we're on C1? Not the derivative, careful. It's cosine t, isn't it?
Yeah.
It's cosine t. So this is sine of cosine t. Please understand, we have to replace the x with what the x component function is, or what the x parametric equation is. So it becomes sine of cosine of t. And then, what does dx really mean? It's the square, but this is the special one, right? But, yeah, when it's dx, it's just x prime, right? And when it's dy, it'll be just y prime. Okay. Yeah, this one right here. So what's dx for us here? Negative sine t is going to go right here. I'm going to put it right here. Negative sine t dt. Y'all all right with that? That's just this, right?
Yes, sir.
Okay. Plus, now, I'm going to do it as a separate integral, even though I don't have to. 0 to pi. I'm going to do this now. And what's that? Cosine of y, but what's, right? Because we're doing cosine of y. What's y for us? We're still on C1. Sine. Cosine of sine of what? Oops, sorry, I didn't mean to put that. Sine of t. And then dy. What's dy for us? Cosine t. dt. All right, I'm off. Definitely off camera there. Questions on that? That's just the first one, right? That's just this one. Then I need plus. Now I'm going to do that one. Do that one over here. I'm going to go ahead and erase this. So we have plus. Now this integral, C2, is going to go from 0 to 1. And now I have sine of, what's x for us here on this one? Negative 1 minus t. And then what is dx? What's dx for us? So what's the derivative of our x here? Negative 1 dt, right? That one. And then I'm going to do a separate integral, plus integral from 0 to 1. And now I have cosine y. Cosine, what's y for us? Is 3t. And then y prime, 3 dt. There we go. Those three integrals. Those three integrals. I think I can do these. Let me do them one by one here. At least set them up. How would you do this integral? This is sine of, right? This is being multiplied. Right. How about a basic u sub? U is cosine. There's its derivative, right? This just becomes sine u. What's the antiderivative of sine u? Negative cosine u, right? Negative cosine u. So this should be negative cosine of u, but u was cosine of t, and that should be evaluated from 0 to pi. And then plus, this is the same thing, isn't it? Except this time it's, so it's sine of t, 0 to pi. See, this time u is sine. There's a derivative. So this is really antiderivative of cosine of u, which is going to be sine of u, and then you evaluate. and then plus, let's do this one. Do y'all see all of these are working the same way? Because this is our basic u sub, u, and then, okay, so this would be negative cosine of -1 up minus t, evaluated from 0 to 1, and then plus negative cosine, sorry, not negative cosine, sorry. This one is sine of 3t, evaluated from 0 to 1. And then we can just plug in and get all these answers. What do you think? All right, what seems to you all to be the challenging part? Is there anything you see as tricky? The C1, C2, maybe? Let's get back to your question from the beginning. What if we wanted to draw it this way, like this? Anyone know how to do this? If we want to go from -1, 0, there's a couple of ways to do it, so I'm curious if we can come up with a way. Come up with an x of t, bless you, x of t, y of t. Oh, I'm not going to finish those. Is that all right?
Yeah.
Those just plug in. Okay.
We still need sine and cosine, right?
We'll still need sine and cosine, yes. But you want, when you plug in, we want our t, let's try and make it where our t still goes from 0 to pi. Let's see if we can do that. So when I plug in 0, I need this to, when I plug in 0 for this, I need to spit out what? -1? You want to try negative cosine? Negative cosine t. So plug in 0, what do you get? -1. Then you want this to be 0, right? At both? You could still use sine t, couldn't you? Because sine of 0 is 0, sine of pi is 0. That should still work. Now, what happens when you plug in pi in here? You get -1 is positive. So that should work. It's a pretty simple change, right? All you're doing is really like reflecting the x component and just flipping it over. All right. Like I said, there are other ways you can do it. You could try like going from pi to somewhere, you know what I mean? Like you could do other things, but it's always nice when we can keep our interval on t something that we're used to working with, 0 to something. All right, we're continuing. All right, so there's a question now that we've talked about this. Does it matter if we do a line integral? Does the direction matter that we traverse that curve C? So, you know, if I say that C is the curve that goes from A to B, right? We call that C. Then the curve that goes backwards would be called negative C. So you see the way we're traversing those? Backwards, right? So any